Hello, everyone. I'm Anais. I'm a first year PhD student at the University of Cambridge, and I'm super excited to be talking to you about SOPEVS today, which is a joint sizing and operation algorithm for PV, EV integrated modern homes. And this work has been done in collaboration with my supervisor, Kasha, who is sitting over there. So please lean back, digest your lunch, and let me start by telling you a short story. Maria is a young professional and has recently bought a very nice single family house. She has also decided to get an EV and she is charging it from home. She really likes it and she's very happy about her choice. But after a few weeks, she opens her mail and is very shocked when she realizes how high her electricity bills are. She talks to her neighbors and hears that they recently got PV panels and a stationary battery, and that they're actually saving a lot of money on their electricity bills. The neighbors then suggest that Maria maybe also should get PV and maybe even a bidirectional EV charger. She had never really heard about this before, but the neighbor explains that it basically allows you to discharge your EV at night and use it as a stationary storage when your EV is at home. And as we've heard in the presentation from yesterday, this is becoming increasingly available with utilities like Octopus Energy in the UK already starting to offer these kind of tariffs. She's thinking about this, but then she realized that she uses her EV to commute to work, and so that it's actually not at home on most days. And she's wondering if it's even worth to get this bidirectional charger. She also heard that solar and storage can be quite expensive, but it really depends on the capacities that you need. So she's wondering how many panels and how much storage would she actually need for her house? One panel and one stationary battery, which can cost as little as $5,000, or maybe 5 PV panels and 2 storage units, or even 10 PV panels and 3 stationary batteries, which can cost more than $30,000. We call this problem a finding the PV and stationary capacity for a specific household a sizing problem. And another question that Maria is asking herself is, how much of her load could she then satisfy with the energy generated from the PV panels? We call that number the self-consumption percentage. And Maria could, for example, say that her goal is to meet 70% of her load for solar energy. Another question that Maria is asking is, when would she need to charge and discharge her stationary battery? And what about the EV? And how can she ensure that her EV is charged enough in the morning when she wants to go to work? And how can she ensure that her battery is not degraded and that it's not charged to more than 80% or lower than 20% of the EV battery capacities? We call this problem the operation problem. Maria is really confused with all these questions in her head, and she's actually not the only one. Many homeowners across the world face very similar questions as Maria, and this has led us to ask the following question. How can we reduce the upfront cost of solar and storage and help users on a personalized level to allow more people to upgrade their homes? And the key idea here is that we really want to reap the benefits of beneficial user lifestyles and make sure not to oversize the system if not necessary. And here in this work, we focus on CapEx, but this can easily be extended to OpEx. So there are 3 trends that motivated our research. In the past, people commuted to work, so we call this work from work. People didn't use PV, but only used the grid, and people mainly used fossil fuel-powered cars. This is changing. More people work from home since COVID, more people have PV, and more people get EVs, but usually still with unidirectional charging. This is going to continue in the future, and then we'll soon reach a point where work from home will become a real possibility in many jobs. More people will get PVs, and bidirectional EV charging will also get more popular. Okay, let's briefly make an excursus and talk about synergies. So here we have a plate of plain pasta, which is pretty boring. We have a plate of plain sauce, which is also pretty boring by itself. But if you combine them both, you get this very nice synergy of pasta with really good sauce, which tastes really good. The main idea behind our work is to also, similar to the pasta with sauce, use synergy benefits that exist between work from home, PV, and EVs. Because basically, when all these 3 trends are aligned, you generate PV energy during the day, your EV is at home because you work from home, the solar energy can be directly fed into your EV, and then if you have bidirectional EV charging, you can use that energy at night to power your cooking, for example. So if you remember nothing from this talk, I just want you to remember one thing, that basically when you have all these 3 together, it's much better than if you have any of them alone. And the key idea behind our algorithm is really to use these synergy benefits and design the cheapest, but also most robust energy systems on an individual home level. This is something that hasn't really been done before, and also shows that it's key to take into consideration the user behavior when designing energy systems. Okay, so the big question is, what is the cheapest combination of solar PV and stationary storage that will meet self-consumption goals, efficiently integrate EVs, and leverage benefits of working from home? This is actually pretty difficult. Why is this difficult? Because first of all, we have time-varying stochastic and non-stationary loads, solar generation, and EV usage. Also, we don't know what the future inputs will look like. And efficient EV charging is complex. And then when you add the discharging component, it's even more complex because, as we've also heard in other talks, the space of the charging solutions becomes really large. Also, discharging comes with a risk of low state of charge levels at departure times. And many users have low risk tolerances for this. And then lastly, we also have lots of different user behaviors that we need to be able to take into account. Okay, so 3 messages that I already want to motivate before I dive into the algorithm is, first of all, we need a personalized design approach because work from home and the EV type really impact the final sizing recommendation. Second, we need to do joint sizing and operation, as the choice of the operation policy is really important, as you're going to see. And then thirdly, if you have some degree of working from home and then bidirectional EV charging, you can sometimes even totally omit the stationary battery. Okay, so briefly, related work falls into 2 broad categories. They mainly either focus on just sizing or just operation, and there's very little work that does joint sizing and operation as they're coupled, and that's why it's really complex, because basically the sizes of the components influences the operation policy, but then you need the operation policy to compute the sizing. Okay, let's talk about SOPEVS. So what are the inputs? First of all, we have the hourly load profile, which is basically determined by human behavior, and that's highly variable across homes. The hourly traces are from past usage, and this becomes increasingly available from smart meters. But if you don't have access to it, there are many countries that have typical profiles or foundation models, like the Faraday Foundation model from Octopus Energy for the UK, for example. In this paper, we work with residential load profiles, but this can easily be extended to commercial buildings as well. The second input is the hourly traces for the solar load profile. Then the third thing we consider is the EV usage, and we want to know the work from home frequency, the typical commuting and non-commuting distances and times, and the EV type. And then we also consider the operation policy as an input, and then there's a bunch of other parameters that you can refer to in the paper. The outputs are then the recommended PV capacity size, recommended stationary storage capacity size, and then the total cost of the system. The objective of SOPEVS is to find the cheapest sizing that satisfies a quality of service requirement, which is expressed using 3 parameters. So first, we have the confidence interval, which we use to ensure robustness. So we want to make sure that the quality of service should not be violated due to small variations in the weather conditions or the load, for example. Then we have the sample period T, and lastly, the loss target, which is the expected unmet energy over the period T. So as an example in English, we can say that we are 95% confident that over any 100-day period, the system can meet over 90% of load. Okay, let's talk about the operation policies. So we have a set of 3 predefined expert policies that trade off efficiency and risk and are both available for unidirectional and bidirectional EVs. But the work is not limited to just these 3, so you can expand it with any policy that you would like. The first one is the naive and standard unoptimized approach that most EV users use today. So basically, they charge the EV as soon as it gets home. The second one is the solar-only approach, which really aims to maximize the use of solar energy, and you only charge your EV from solar energy, but that comes at a risk of not fully charging it until the next departure. And then there is the hybrid approach, which we call solar and grid. And basically, it still tries to maximize solar usage, but it also wants to ensure high EV charging levels at departure times. So solar only is extreme, and solar grid is what we advocate. Yeah, as you can see, the operation policies are actually quite complex. You can find more details in the paper, but basically the main differentiation between them is how they prioritize charging and discharging and how they deal with user risk tolerances. Okay, so how does the algorithm actually work? We use a synthetic data generator from our prior work called Spaghetti that allows to generate hourly EV usage for different locations and commuter types. And then in the first step of the algorithm, we take a number of subsamples from the PV trace and then the corresponding load and EV traces, each of length equal to t, as you can see here on the graph. We do this subsampling basically as a statistical bootstrap, and this creates a set of n subsamples that span multiple seasons. We call each of these samples a scenario and then treat their ensemble as an estimate of expected future scenarios. Okay, in the second step of the algorithm, we compute the minimum cost feasible sizing for each subsample, and we use stochastic gradient descent. This is inspired from prior work from Huang et al. So basically, for each pair of PV allocation, we compute the minimum battery needed to achieve the quality of service requirement. Here you can see the graph that displays the search and the total cost of the system indicated by the color. We directly want to find the minimum cost sizing here for each subsample, and here the minimum cost sizing is marked by X. This is a smooth surface, so we can use stochastic gradient descent, and we use ADA delta as it works well without needing to fine-tune the hyperparameters. And then in the third step, after finding the minimum sizings for each subsample, we compute the final result. So in the figure here, each of the blue and red dots represents one of the minimum cost sizings coming from a subsample. And if we want to make an analogy with an egg, the sizings that we computed with known data are like the egg yolk. But because our final result sizing would need to deal with unknown data in the future, we want to be robust and leave a buffer, like the egg white. And then we want to offer a sizing on the egg shell that is the minimum cost. So if we want to find the location of that shell, we can use multivariate Chebyshev bounds, which is a concept that we know from statistics. Each individual sizing is then treated as a sample from a set of IID distributed random variables, which stem from the variations in PV, load, and EV usage. And then once the bound has been computed, which is the yellow dome here on the graph, we find the minimum cost sizing on a Chebyshev bound, which is marked by X here. Okay, let's talk about the results. So we have conducted an experiment with 20 homes from Texas and a Nissan Leaf EV. And the first main result is that the work from home and EV types heavily influence the sizing decisions that we get. The baseline here is the naive operation policy with no work from home and no bidirectionality. So what most people do today when they compute sizing. And if we focus only on the third result in the interest of time, basically, if we include both bidirectional charging and 2 work from home days, we can save more than 30% on the CapEx. This clearly shows that users may oversize their system and pay much more than necessary if their lifestyle benefits are not taken into account at the design stage. The second big result is the importance of doing joint sizing operation. So the idea is that for a fixed work from home type and fixed EV charging type, we can reach even important savings by just choosing the right operation policy. So if we again only focus on the second result, for users with bidirectional charging who use the solar-only policy, they can achieve more than 80% of CapEx savings. But you will likely not finish to charge your EV. So this is a consideration that you need to make. Okay, and then thirdly, we really recommend to use some sort of work from home frequency and bidirectional charging if available, because as we can here see, by just adding bidirectionality, we can reduce the required battery size from 12 kilowatt hours to 7 kilowatt hours. And then if in addition we introduce 2 work from home days, we only need a battery that is 2 to 3 kilowatt hours large, so really, really small. And therefore, we really recommend the solar grid bidirectional policy with 2 work from home days. We have built a web app that allows homeowners to use SOPEVS so that they can get more clarity on the sizings that they need. It works for users from all over the world who have access to their past load data, and then also for users for the UK who don't have access to their load data because we integrate with the Faraday model from Octopus Energy. To summarize the most important points again, first, we need highly personalized approaches to design our home energy systems So here I really mean the work from home lifestyle, the desired self-consumption, and the percentage and the risk tolerance. Second, we need joint sizing and operation to really capture all benefits of a specific user lifestyle and setting. And then thirdly, we advocate the use of bidirectional EVs combined with some degree of work from home. Things have really changed since COVID, and we should really think about how to leverage individual user lifestyle benefits to make our systems more efficient and cheaper. And this is something that anybody working in buildings should remember, that we really need to take this into account in the user behavior. Yes, and if you want to try out the tool here, you can find the link. Let me know if you have any thoughts on the tool, and if you want to reach out, here you can find my website. And yeah, thank you. I'm happy to hear your questions.